Dear students, in previous class we discussed about Lagrange's theorem. What is Lagrange's theorem? The theorem states that for any prime p and if f is a polynomial of degree n, then fx congruence to 0 mod p has at most n solutions. Also we see that the Lagrange's theorem does not hold for a congruence relation for when its modulus is a composite number. Now in this class, let us discuss about the application of Lagrange's theorem. If f of x equals, consider a polynomial, if f of x equals c0 plus c1x plus etc plus cnx power n be a polynomial of degree n with integer coefficients, and if the congruence f of x congruence to 0 mod p, then it has 0 mod p has more than n solutions where p be a prime, then every coefficient of f is divisible by p. If this relation has more than n solutions, then p must divides every coefficient of f is divisible by p. Means p must divide its coefficient. All of its coefficients are integers. So how to prove this one? So consider a polynomial that f of x that is the given polynomial. F of x equals c0 plus etc plus cn x power n be a polynomial of degree n with the integer coefficients. And if the congruence f of x congruence to 0 mod p, consider the congruence f of x congruence to 0 mod p has more than n solutions, then we have to show that each of these coefficients must be divisible by p. And we assume, suppose sum of its coefficient does not divisible by p, means p does not divide sum of its coefficients. So let there exist some coefficient does not divisible by p, and let ck, that's our assumption, let ck be the coefficient, sum of the coefficient with the largest index, then c0 plus c1x plus c2x square plus etc plus ck x power k. Consider this polynomial where ck be the sum of its coefficient does not divisible by p. You can choose ck be the coefficient in such a way that p does not divide ck. Then consider the polynomial c0 plus c1x plus c2x square plus etc plus ck x power k. So, and suppose this is g of x. Then that means this g of x congruence to 0 mod p has at most k solutions. Why? Because by Lagrange's theorem. So it has, if it has more than, then it has more than k solutions, then by Lagrange's theorem p must divide ck. P must divide ck, comma, a contradiction to the choice of this one, hence this contradiction is due to our wrong assumption. Therefore, every coefficient must be divisible by p. Okay, we assume, suppose there exist some coefficients not divisible by p, so let ck be the largest index, vk be the some coefficient of largest index, then c0 plus c1x plus c2x square plus etc plus ck x power k congruence to 0 mod p has more than k solutions. But by Lagrange's theorem, p divides ck, that's a contradiction to the choice of p. This contradiction is due to our wrong assumption. Therefore, p must divide all of its coefficients. Enough. Okay. So now consider another result. For any prime p, all the coefficient of the polynomial f of x equals x minus 1 into x minus 2 into etc into x minus of p minus 1 means x minus p plus 1, x minus of p minus 1 minus x power p minus 1 plus 1 minus x power p minus 1 plus 1 is divisible by p. For any prime p, the polynomial f of x equals x minus 1 etc. into x minus of p minus 1 minus x power p minus 1 plus 1 are divisible by p. How? Come to the proof. Let g of x equals, consider a polynomial, let g of x equals x minus 1 into x minus 2 into etc. into x minus of p minus 1. Consider this polynomial. Means the roots of g. What are the roots of g? Roots of g are 1, 2, 3, etc. to p minus 1. Okay. Means this 1, 2, 3, etc. to p minus 1 are satisfies the congruence relation g of x congruence to 0 mod p. That is the linear congruence. G of this 1, 2, etc. to p minus 1 are satisfies the polynomial or sorry, the linear congruence g of x congruence to 0 mod p. Then the numbers, consider the numbers set of all x such that x of all in set 1, 2, 3, etc. to p minus 1, etc. to p minus 1, then which satisfies a congruence relation from how? From where? That is by, yes, Euler-Fermat theorem. Euler-Fermat theorem states that x power p minus 1 is congruent to 1 mod p. Okay. Set of all the numbers which are fallen, set of the numbers set of all x such that x of all in set 1, 2, 3, etc. up to p minus 1. That satisfies this congruence relation x power p minus 1 congruent to 1 mod p. This is from Euler-Fermat theorem. That means x power p minus 1 minus 1 is congruent to 0 mod p. Agreed. So, let consider a polynomial. Let h of x equals x power p minus 1 minus 1. So what do you get from here? You have h of x congruent to 0 mod p. Agreed. Here g of x congruent to 0 mod p and h of x also congruent to 0 mod p. So now consider f of x. Let f of x equals g of x minus h of x. G of x minus h of x. What is g of x? G of x is congruent to 0 mod p and h of x is also congruent to 0 mod p. So g of x minus h of x is also congruent to 0 mod p. That means f of x congruent to 0 mod p. Okay. F of x congruent to 0 mod p. That is x equals 1, 2, 3, etc. to p minus 1. That means f of x congruent to 0 mod p means x equals 1, 2, 3, etc. to p minus 1 should satisfy the relation f of x congruent to 0 mod p. That means f of x congruent to 0 mod p has how many solutions? P minus 1 solutions. Yes, p minus 1 solutions. But what about f of x? But f of x be a polynomial. What is f of x? G of x minus h of x. This is g of x and x power p minus 1 minus 1. This is f of x. What is f of x? F of x be a polynomial of degree p minus 2. But f of x be a polynomial degree p minus 2, then by the application of Lagrange's theorem, each polynomial of f of x must divisible by p. Each coefficient of f of x must divisible by p. Okay, so that is what we repeat. Enough? Consider g of x. From here, clearly g of x is congruent to 0 mod p. Why? Because by the choice of g of x, as well as the set of all x, where x of all in 1, 2, 3, etc. to p minus 1, that satisfies this congruence relation because from Euler-Fermat theorem. So x power p minus 1 minus 1 is also congruent to 0 mod p. But what is h of x? That h of x is x power p minus 1 minus 1. Then f of x equals g of x minus h of x by the choice of g of x, h of x and the given f of x. Then from here f of x congruent to 0 mod p. That means x equals 1, 2, 3, etc. to p minus 1, which satisfies this linear congruence f of x congruent to 0 mod p. Okay, but so means f of x congruent to 0 mod p has p minus 1 solutions. But what is f of x? f of x be a polynomial of degree p minus 2. Hence, by the theorem, each coefficient of f of x must be divisible by p. Okay, right. Now we consider the next important result. That result is known as Wilson's theorem. What is Wilson's theorem? Wilson's theorem states that for any prime p, p minus 1 factorial is congruent to minus 1 mod p. So this is Wilson's theorem. Wilson's theorem is a very important theorem. The theorem says that for any prime p, p minus 1 is congruent to minus 1 mod p. How? So, consider a polynomial. For its proof is in this way. Consider a polynomial. F of x equals x minus 1 into x minus 2 into etc. into x minus etc. into x minus of p minus 1 minus x power p minus 1 plus 1. Consider this polynomial. F of x equals f of x minus 1 into x minus 2 into etc. into x minus of p minus 1 minus x power p minus 1 minus 1. So, the constant term of this polynomial, what about the constant term? Its constant term is, what is the constant term of this polynomial? 1 into 2 into 3 into etc. to p minus 1. Okay, minus of this one means p minus 1 plus 1. Enough? So, the constant term is 1 into 2 into 3 into etc. to p minus 1 plus 1. That means it is p minus 1 factorial plus 1. Enough. But what is the previous theorem? According to previous theorem, it consider for any prime p and the polynomial f of x equals x minus 1, x minus 2, etc. x minus of p minus 1 minus x power p minus 1 plus 1. All of its coefficients are divisible by p. Here the constant term is nothing but p minus 1 factorial plus 1. So we know that p must divide this p minus 1 factorial plus 1. That means p minus 1 factorial is congruent to minus 1 mod p. That is p minus 1 factorial plus 1 is congruent to 0 mod p. That means p minus 1 factorial congruent to minus 1 mod p. This is Wilson's theorem. So this Wilson's theorem heavily depends upon the theorem which has been already stated. Okay, right. Now come to the converse of Wilson's theorem. What about the converse of Wilson's theorem? Do you say the converse is true? Just we check it. If n minus 1 factorial, the converse of Wilson's theorem states that if n minus 1 factorial is congruent to minus 1 mod n, if n minus 1 factorial is congruent to minus 1 mod n, then n is prime if n greater than 1. Then n is prime if n greater than 1. So is this converse of Wilson's theorem. Wilson's theorem states that for any prime p, p minus 1 factorial plus 1 is congruent to 0 mod p. And the converse of Wilson's theorem says that if n minus 1 factorial is congruent to minus 1 mod n, then this n is a prime number. This n is a prime number when n greater than 1. How? So, the proof is in contradiction method. We can assume, first assume n is not a prime, means n is composite. n is not a prime means n is composite. Okay. So, when n is not a prime means n is composite, we have to show that n minus 1 factorial is incongruent to minus 1 mod. Not by contradiction. Sorry. Here there is a correction. The proof is not done by a contradiction method. It is in another way. It is contrapositive, means when we have to show that n minus 1 factorial is congruent to minus 1 mod n, then n is prime. We consider this as if n is not a prime. If n is not a prime means if n is composite, then we have to show that this n minus 1 factorial is incongruent to minus 1 mod n. That is what B requires. So let n is composite. Here n greater than 1. Then the next prime is 2 and 3. After this 1, 2 and 3 are primes. So we start from when n greater than 4. Greater than or equals. When n greater than or equals 4. If n equals 4, what happens? When n equals 4, what is 4 factorial? 4 n minus 1 factorial. 4 minus 1 factorial. What is 4 minus 1 factorial? 4 minus 1 factorial is 3 factorial. 3 factorial means 6. 6 is incongruence to minus 1 mod 4. When n equals 4, so n minus 1 factorial means 4 minus 1 factorial, that is 6 factorial. 6 factorial is 3 factorial. 3 factorial means 6. 6 is incongruence to minus 1 mod 4. So when n equals 4 means n is a composite, n minus 1 factorial is incongruent to minus 1 mod n. Now when n greater than 4. When n greater than 4. When n greater than 4, if possible, there are two conditions, two cases. Suppose n equals a into b. A into b, where 1 less than, a less than, b less than n. Then what is n? Minus 1 factorial. But we know that minus 1 factorial is 1 into, 2 into, 3 into, etc. to n. That is 1 into, 2 into, 3 into, etc. to a into, b into, etc. to n. Okay? Yes. That means n minus 1 factorial equals 1 into, 2 into, etc. to a into, a plus 1 into, etc. to b into, b plus 1 into, etc. to n. Okay. Yes. That means it is AB into, okay, AB into 1 into 2 into etc. to A plus 1 into etc. to B plus 1 into etc. to n. But is A, B, they are also integers. So AB into this one. So n minus 1 factorial is nothing but n into, what is AB? As by the choice, n equals AB. So n into 1 into 2 into etc. whatever may be, it is nothing but a lambda. So from here, that means n minus 1 factorial is n into a multiple of n. That means n minus 1 factorial. Yes, n minus 1 factorial is a multiple of n. Means n divides n minus 1 factorial. That means n minus 1 factorial is congruence to 0 mod n. So that means n minus 1 factorial plus 1 is incongruence to 0 mod n. Okay, that means n minus 1 factorial is incongruence to minus 1 mod n. So when n equals 4, n minus 1 factorial is incongruence to minus 1 mod 4. When n greater than 4 and if n is a product of any two primes, then also is n minus 1 factorial is incongruence to minus 1 mod 4, minus 1 mod n. Agree. Now consider the second case. When n is p square, what happens? Here n equals ab, n equals 4, the result of n minus 1 incongruence to minus 1 mod n. When n equals ab, again n minus 1 is incongruence to minus 1 mod n. Now next case is when n equals p square, square of a prime. When n equals p square, where p be a prime, square of a prime. So we have, since n greater than 4, now consider the next case, n greater than 4. That is, when n greater than 4, surely p greater than 2. Why? Because n equals p square. Since p greater than 2, we have p square minus 1 greater than p square minus 1 strictly greater than 2p. Okay, then since p greater than 2, p square minus 1 greater than 2. Now consider p square minus 1 factorial. What is p square minus 1 factorial? It is 1 into 2 into etc. to p square minus 1. Agree? That is nothing but it is 1 into 2 into etc. to p into etc. to 2p into etc. to p square minus 1. Why? Because p square minus 1 should be greater than 2. Enough? Okay. That equals, means it is 1 into 2 into etc. P minus 1 into P plus 1 into etc. into 2P into etc. into P square minus 1. Instead of 2P, here the previous term is 2P minus 1, 2P plus 1. So that is, take this P and P outside, that is P square into, what remains 1 into 2 into etc. to P minus 1 into P plus 1 into etc. up to here 2 into etc. to P square minus 1. That means P square into some lambda 1. Agree? So that means P square minus 1 factorial is congruent to P square multiple of P square. That means P square minus 1 factorial is congruent to 0 mod P. Okay. 0 mod P. Mod P means, 0 mod P means what is P? P square. P square is n. That means n square minus 1, n square, n minus 1 factorial is congruent to 0 mod n, since P square is n. That means n minus 1 factorial is, n minus 1 factorial plus 1 is incongruent to 0 mod n. That means when n equals P square, n minus 1 factorial is also incongruent to minus 1 mod n. Hence, if n is composite, n minus 1 factorial is incongruent to minus 1 mod n. That means n minus 1 factorial is congruent to minus 1 mod n only when n is a prime number. That is what we require here. This is the converse of Wilson's theorem. Agree?